Next, we're going to look at inverse functions, and inverse functions sort of undo what you just did. For example, if you're at home and you come to school, if let's say this is your function f, its inverse will basically take you from school back to home. So it kind of undoes what you just did. The function will take you to school. The inverse will take you from school back to home. For example, let's say a function adds 5 to its inputs. So f of x, a function, will take his input x and add 5 to it. Its inverse would have to do the opposite. So its inverse takes the input and subtracts 5 because it has to undo what was done here. So f inverse, that's how it's read. F inverse, there's a power of -1, but it's really not a power. It's a notation that is read F inverse. Would have to take the input and then subtract 5 from it. So the function takes the input and adds 5, and the inverse takes the thing and subtracts 5 from it. Let's quickly test it out. Let's give the function f a value of 5, so a value of 9, I'm sorry. I'm going to give it 9, so f of 9 is going to be the input plus 5, which is going to give me 14. So I gave it 9 and the output was 14. That's the ordered pair that was created. Now if these two functions are really inverses of each other and undo each other, when I give f inverse 14, it better take it back to 9 because it's the inverse function. Let's test it out. F inverse of 14, if I give it 14 and I put it in there, what does it spit out? 9. So I got the ordered pair input 14, output 9. The function takes 9 and puts it at 14, and the inverse takes 14 and puts it back at 9. These two are inverses of each other. Some facts to know. A function f has an inverse if it is 1-to-1. This means that different inputs always give different outputs. So each x has only one y, and each y has only one x, meaning x's don't repeat and y's don't repeat. Is this a 1-to-1 function? 1 is only associated with 2, 3 is only associated with 6, and 9 is associated with 5, so my answer would be yes. Each input gives a different output. Each x only has one y, and each y has only one x. Part B, 1 is associated with 2, 3 is associated with 6, but then all of a sudden, 9 is also associated with 2. So y's are repeating, and the inputs are giving the same output, so this would be a no. This is not a function. Or it is a function, I'm sorry, but it is not a 1-to-1 function. Remember, for a function, all the x's should have not repeated, and each x should have only had one y. Now it's stricter. Each x only has one y, and each y has only one x. Also important to keep in mind that graphically a 1-to-1 function passes not only the vertical line test because it's a function, but also the horizontal line test because now it's a stricter function where x's and y's completely have different partners, I guess, associated with them, you can say. Let's look at these and see if they are 1-to-1 functions. So it passes the vertical line test because it's a function, so it will pass that for sure. Now it has to pass the horizontal line test for it to be a 1-to-1 function. So if I'm focusing on the red graph, every time I take a vertical line and I go through it, it only touches it once. So that's a yes. Again, horizontal line test means all horizontal lines going through my red function should only touch it once. Let's see for part B. If I take a horizontal line and a vertical line, of course, it's always touching it once when I go through it. But notice when I look at horizontal lines, it's touching it twice. So this would be no, it's not a 1-to-1 function because both of these x values share the same y value. Both of these x values share the same y value up here. Part C, of course, it passes the vertical line test because it's a function, but for 1-to-1ness, it has to pass the horizontal line test, and every time I go through it, it only touches it once horizontally, so that's a yes as well. Another important fact is since f inverse undoes f the function, their domains and ranges are always going to be switched. This is what I mean. Let's go back up over here. Remember how I gave the function 9 and it gave me 14, so 9 went to 14. But then when I gave the inverse, what we thought was the inverse, the 14, it landed it back at 9. So it took this ordered pair that came from f and it simply switched it. This was the ordered pair related to f, and this is the ordered pair related to f inverse. The x became a y and the y became an x. So that's an important fact to know, along with number 1, which is a function has to be 1-to-1 for it to have an inverse. The second fact is two inverses always have their domains and ranges switched. Let's look at an example. It says find the inverse of f given below, then list the domain and range of f and f inverse. So here's the function. If I don't know what the function definition actually is, and I just have those distinct points, I know that the inverse will just take those ordered pairs and simply switch them. So it'll take 5 and put it at 0, it'll take 9 and put it at 1, and it'll take 13 and put it at 2, and it'll take 17 and put it at 3. So simply the only thing we did for the inverse was to switch the x and y values. Here is the original inputs, here's the outputs. The inverse takes all the outputs, makes them act like the inputs, and then gives you the outputs to be the original inputs from the other function. So in other words, 0 goes to 5, that's the function, and then the inverse takes the 5 back to 0. So what's the domain and the range of each? Well, the domain of this is 0, 1, 2, 3. And the range of f is 5, 9, 13, 17. And notice, logically, it makes sense that the domain of this is exactly the reverse or the opposite of what the other one was. And the range of this is 0, 1, 2, 3. So domain of f became the range of f inverse, and the range of f became the domain of f inverse. Their domains and ranges are always switched because to get the inverse, all you have to do is switch the x and y. How do we formally find the inverse of a function? The first thing, we want to make sure that the function is 1-to-1. So in other words, make sure it passes the horizontal line test if you can get a quick graph of it. Then you switch the x and y because that's essentially what inverses do. Then you solve for y and you call the y your inverse function. Let's do a quick example. Find the inverse of f of x equals 2x. Well, I gotta make sure this is 1-to-1, so I think in my head, well, that's just a line with y equals mx plus b, so it looks like a line going through the origin, and yes, it is gonna be 1-to-1, which means I can find the inverse. So 1 is checked out. Remember, f of x is just a y value, so this is the graph or the equation I'm looking at. Next thing I'm going to do is switch the x and y, so y becomes my x and x becomes my y, and then solve for y. Well, that's going to be fairly quick. Divide by 2, and so y is equal to x over 2, and then the very last step, call it your inverse function. So f is what I started off with, f inverse must be x over 2. Now let's think this through. F of x takes the input and doubles it, and we went through these steps and we found f inverse to be x divided by 2, so it halves the input, which makes sense. If I multiply something by 2, the inverse function better take the thing and divide it by 2. So we didn't have to go through the steps. We could have almost guessed that if the function doubles it, multiplies it by 2, the inverse must divide it by 2. This was a quick one that we could have logically thought through as well. Let's find the inverse of g of x equals a third x plus 3. Again, this is y equals mx plus b, which is a line, so it is 1-to-1. I don't have to worry about that further. Next thing I'm looking at is really y equals 1/3 x plus 3, and I switch the x and y values, switch their roles, and then I'm going to solve for y. So I switched the x and y, and then my next step was solve for y. So I'm going to multiply everybody by 3 to get rid of that fraction to solve for y. That's going to give me 3x equals y plus 9, and then I subtract 9 from both sides, and that's going to give me y equals 3x minus 9. So there is my inverse. G inverse of x, since my original function was a g, is actually 3x minus 9. Find the inverse of p of x equals x minus 5 over 2. Again, this looks like y equals mx plus b, because if I simplify it, p of x could really be x over 2 minus 5 halves. So this is 1 to 1 because it's a line. Since it's 1 to 1, I really have y equals x minus 5 over 2 to work with. So I switch the x and y values, and then I solve for y. So multiply both sides by 2 to get rid of the fraction. 2x equals y minus 5. We're almost there. Add 5 to both sides, so we've got y equals 2x plus 5, and I'm going to call this my inverse function. So p inverse of x is 2x plus 5. Notice how these inverses work. P takes the x, subtracts 5, and then divides the result by 2. That's what the function is performing. Subtract 5, then divide the result by 2. The inverse just retraces those steps backwards, takes the input, doubles it, then adds 5. So here's what happens. Take the input, subtract 5, divided by 2. The inverse simply says go backwards, multiply by 2, and then add 5. Multiply by 2 or double it, and then add 5, and that's how we're getting the inverse from the original function, just retracing our steps backwards. Subtract 5, then divide by 2. The inverse says, no, multiply 2, then add 5. And that's how we're getting the inverse also. But a sure way is just to switch the x and y, and then solve for y, to make sure you don't make any mistakes in the process of thinking of it just backwards, retracing your steps. The last little piece of info to know is that the graphs of f and f inverse are reflections of each other about the mirror line y equals x. Because we switch the x and y, they create this mirror image about each other. Let's go look at this example. It says graph f inverse of x, the inverse function, given the original function f of x. So here's f of x, a function, and we have some ordered pairs that I can pull from the graph. I have -4, -4, I have -2, 0. I'm going to use these as a guide, and then I have 3, 4. So these are the ordered pairs for the f function. Remember, the inverse function, all it does is switch their order, because it takes the -2 going to 0, and it takes the 0 and lands it back at -2, for example. So to get the inverse ordered pairs, all I have to do is switch these guys, switch the domain and the range. So these are just a few reference points. You can pick more ordered pairs if you want, but those are the ones they've labeled. So I took the original function f, ordered pairs, I reversed them to get ordered pairs for my inverse function, and notice what the graph looks like. So I still have -4, -4 for my inverse. Then I have 0, -2. Then I have 4, 1, 2, 3, 4, up 3. And if I connect those dots, it looks like I get a mirror image of this blue segment on the other side, and my mirror is the line y equals x. This will always happen with graphs of inverses, because all you simply do is switch the ordered pairs. The reflection always happens across the line y equals x.